So this is probably about where in your research things started to feel like you were making a series of sharp 90-degree angles off the road and it was not connected to anything else. And, you know, I don't understand any of this because it doesn't feel like it's connected. What am I doing? Why do I have to know? What? Who? He did what? This is like crazy physics. Yes? Any of you have that sensation? There's a reason for that. We're going to make 3 sharp 90-degree angles off the road. If we make 1, 2, 3, we're going to make 4 of them. So we'll end up back on track, but we have to go through 4 90-degree turns off in the brush first. It's okay. Just buckle up. So we're going to talk about visible light. The slide that I don't have that you have in your notes is the problem that still hasn't been solved. Is that question that Rutherford has. Back to those darn electrons is the slide. Why aren't the electrons sucked into the nucleus? Why does that not happen? Cheating. Thanks. So there are, thank you, you can have it back now. This is where we leave the realm of chemistry and the atom strictly for a little while, and we journey into other physical phenomena and other physics research that's happening, which influences discoveries that happen about the atom. That's why some of these ideas seem very unconnected, because they're not tightly connected. They're tangential, but they influence what we know about the atom. So you have to at least have a glancing understanding of them to understand what we're going to talk about with the atom. So let's talk about visible light, okay? Shall we? This is our first 90-degree turn off the road, into the brush and the mud. Woohoo! Buckle up. You're all sitting bathed in visible light. You probably know, but maybe you don't, that it's part of this larger spectrum of energy called the electromagnetic spectrum. Sometimes called the EM spectrum, EMR, electromagnetic radiation. Not the same as nuclear radiation at all, but it's these energetic waves, and light is one of them. And this is the whole spectrum here, and it's beautifully done in your book. You can see a nice picture of it. And it goes from really big, massively long waves up to, waves that are way beyond the limits of mental comprehension. And the visible light spectrum, all the light that we know, is this one little tiny piece of the spectrum. It's minuscule. And all the light that you've ever seen, the red, the orange, the yellow, the green, the blue, the indigo, the violet, bouncing off things, combining in different patterns so that we see more colors than just those 7, is part of this spectrum. We've known for a very long time that light behaves as a wave. Newton figured this out. Newton was a whack job, let me tell you. The man was pretty weird, and he was an alchemist. He actually subscribed to a lot of alchemical stuff too, which probably contributed to some of his weirdness. But he did a lot of work with light, and he had posited that light was a wave, and this was pretty well understood. Nobody was doubting this. Well, if something's a wave, there are things about it we can measure. If we take any wave, there's a wave, we can measure its wavelength. So the area from one trough to the next trough is a wavelength, or from one crest to the next crest is a wavelength. We've gone through an entire cycle of motion. We can measure that. If we put an object, we'll put our object over here. If we put an object in the path of that wave, we can count how long it takes, or how many, within a given unit of time, how many troughs hit that object. So how many full wave motions we go through in a unit of time. And that could be hours, minutes, seconds, whatever. That's the frequency. How many waves hit. If you've ever been in a lake that has a dock, or out in the ocean where there's a pier, imagine telephone poles down in the water and waves coming at them. How many waves hit it every second? That's its frequency. So we can measure those things. And we can also measure the wave's speed. Now, we usually think of speed as being velocity, being v as a variable. In physics, when we're dealing with light, we use c to indicate the speed of light, and it comes from Latin or Greek. Anyway, but we use c as an indicator for speed of light. And everything on the electromagnetic spectrum moves with the same speed. It all moves at c. And there's this nice, handy little three-part equation that ties those things together. So for anything that's a wave, we can describe it. We can figure out its frequency, its wavelength, and its speed. Remember I said that this visible spectrum is identified, these different colors. We can actually identify the wavelength of light. Blue is 400 nanometers, and I want to say red is like 7 or 750. I'd have to look it up. I don't commit those to memory. But they have individual wavelengths and therefore frequencies because they're all traveling at the same speed. Cool. Okay, what does this have to do with the atom, Moser? So, we've got individual frequencies that make up given parts of light. Great. We can calculate things about light waves. Awesome. Go buy yourself a cookie. Well, here's where we get back to the parlor tricks. So this might constitute our second sharp 90-degree turn off into the mud and the brush. This is so weird. Parlor tricks, yeah. So if you take a piece of metal and you put some current on it, you know that you can get it to conduct electricity, right? Because metals are good conductors. Fabulous. That's an electrode, basically. If you take a piece of metal and you stick some current on it and it conducts electricity, you now have an electrode. So let's imagine this as a visual, as a high diving board. Here's our ladder. Here's our diving board, down into the water. And lined up on the diving board are a bunch of crazy people who would like to jump off something that's 10 meters in the air and go swimming. Okay, there's our little line. They're packed. You know, front to back, boom, 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 elbow to elbow. So if we imagine that our electrons are very much like this, because on the surface of a piece of metal, that's what you have, is you've got a bunch of these little electrons packed, elbow to elbow. And when you conduct electricity, all you're doing is shoving one of these electrons off the piece of metal. That's all that happens. It's like a garden hose with water running out of one end. So our little electron dives off, you know, if this diving board is our electrode, our little electron dives off the end, and the next one steps up and dives off the end, and the next one steps up, and they just keep doing it, and that's the flow of electricity. Well, the weird thing, because there keep being weird things, is that for a given piece of metal, if we shine a light on it, the electrons jump off of it faster. That's bizarre. So if we take a piece of metal that we're using as an electrode and we shine an ultraviolet light on it, the rate of conduction of electricity increases. So if one little electron is diving off at every second, suddenly 2 or 3 are diving off at every second. So the other part of this is that for specific metals, the light had to be at a minimum frequency. So remember we said, you know, red, orange, green, red, orange, yellow, green, blue, indigo, violet. Above blue in frequency is ultraviolet light, above the violet end of the visible light spectrum. And so this UV light, it has to have a minimum frequency in order to make this work. So you can't just shine any light on it. It has to be a very specific light, a very specific wavelength. This had been known about for a long time. And this was one more of these kind of physics things that people had observed in labs but didn't have a good explanation for. How is this connected to the atom, Moser, for Pete's sake? Okay. Well, this is still part of that second 90-degree turn off into the mud and the brush. Max Planck! There is now the Max Planck Institute in Berlin. The man made a bit of a name for himself. And here, Max Planck is seen discussing his ideas with somebody else. Does anybody recognize from that photo? This is Max Planck. Anybody recognize from the photo who the other guy is? Yeah, it's Bohr. That's Niels Bohr, the Dane, always very somber looking, very serious, very Danish. So in 1900, to explain, so we've kind of backed up in time. This is not straight up timeline stuff because we're now talking a little bit about how ideas built on one another. So in 1900, Max Planck had said, talking about the photoelectric effect, I think that when a material loses energy, so for instance, a piece of metal that's transmitting electricity, it does it in chunks. It does it in actual chunks, pieces, discrete units. We got this theme going, chunks of stuff. So Thomson said that there were little chunks of stuff, and now Planck is saying that materials can gain and lose energy in chunks. He calls them quanta, and that's actually where the term quantum comes from. So a quantum is the individual chunk, quanta is the plural, and a quantum is the minimum amount of energy that you can gain or lose. It's like the penny. You can't spend a half a penny. You can spend 1 penny, you can spend 2 pennies, you can't spend 1.5 pennies. So a quantum is the penny of energy transmission. He comes up with an equation, E equals hv, and E is energy. V is the frequency of a given piece of electromagnetic radiation, and H is this fudge factor that he has to put in. So every single equation is off by the same amount, and he figures, well, if I multiply everything by this number, it all works all the time. Woo! Which seems like cheating, but in fact, he actually discovered a universal constant. So it's not cheating. It's Nobel-worthy. And it's known as Planck's constant. And we actually will use it in a lab that we do after we do the atomic history stuff. We'll do some calculations involving Planck's constant. So now we've got this idea of quanta, discrete chunks of energy. And Einstein takes a look at that. And Einstein looks at Planck's idea and says, well, if light, he takes this idea of energy being in chunks and thinks about light being a form of energy and thinks about chunks of light. A chunk of light. Well, we all know that light is a wave, right? Of course, don't be silly. We've known that for a long time. But Einstein says, no, you know what? I think that light behaves both as a wave and a particle. I think it's a wave, and at the same time, it's a particle. That's weird. But if Uncle Albert says it, he can get away with it. He calls these light chunks photons, so they're kind of in a way equivalent to quanta, that photons are the individual, they're the pennies of light in terms of light chunks. This seems very unconnected to atomic theory. But it lays the groundwork for things we know about the electron. So, you buckled up because we're going to do our next 90-degree turn. Okay, you all look a little tired. That's good for what we're going to do next. So, we've known that if we take a low-pressure gas, so we have a gas in a low-pressure environment, kind of like a cathode ray tube, and we put some current through it, something happens to the atoms. So I would like to invite you all, this is the only time I will invite you to do this ever, to stand up. I'll invite you to do that more often. And to stand on the seat of your desk. Oh, look at you all. Isn't this nice? So, I should take a picture, but I can't figure out how to do that while running the recording. So anyway, if we add energy to an atom, we can kick it up a notch. Okay? So you guys, right now, we're gonna say that we've added some energy to you. We've certainly raised your potential energy, we know that. Where you were at before was your ground state. We hadn't added anything to you. You were just where you've been. And now we've raised you up a level. So this would be your excited state. Are you excited? Woo-hoo! No? Not so much? Yeah, that was kind of weird. Let's pause this. So, from where your feet were at in your ground state, just standing on the seat. Or I'm sorry, from where your feet were at in your ground state, just standing on the ground next to your chair, versus where your feet were at in your excited state. That height difference we talked about, was it the same for all of you? Yeah. Now, if we look at the top of your head, no. Your heads are all different heights. But that's why we're talking about your feet. So there was a specific gap between where your feet were at in your ground state and in your excited state. What does this have to do with atoms, Moser? Come on. Well, this is our third 90-degree turn. It's not really. This is part of the same turn, I think. So if we take a hydrogen atom and we push some electricity into it, we push it up to its excited state. And you know what happens? This is so cool. It glows. It glows a pretty pink. It's this nice soft pink glow. Lovely. You could have a hydrogen lamp at home. All elements have a standard color that they glow when you run energy through them. What color does mercury glow? Mercury vapor when you run energy through it. It's pretty white. It's got a lot of blue in it, but it's got a nice enough mix that it gives us almost white light. That's mercury vapor with electricity running through it. So if we had hydrogen bulbs, it'd be a nice soft pink glow. Well, when we take that nice soft pink glow and we run it through a prism, it breaks it down, and you can see, and they're really tough to see on the overhead. There's a nice image of them in your book. It breaks down into 5 lines, okay? 5 individual frequencies of light. But there are more than 5 frequencies of light. I mean, my God, there's this whole spectrum of light. Where's the rest of it? This is distressing. So Well, this is all the possible frequencies. These 5 lines that hydrogen produces, when you combine them, give us a nice pink glow. But it's just those specific frequencies. Well, remember Planck said that a frequency was related to an amount of energy, E equals hv? So for a long time, a couple questions have been bothersome. Why don't electrons get sucked into the nucleus? Why does hydrogen not emit a continuous spectrum of light when you get it all excited? And what does any of this have to do with the atom? Okay. The new idea that comes up is because, well, it's proposed that the difference, that amount that's the difference between excited and ground, is a quanta. You know, is a single quantum of energy. It's the penny. So the height between the floor and your desk is that smallest amount of energy that can be given off or taken in. And when you light up a hydrogen atom and it gives off energy in 5 different frequencies, well, that seems to indicate something. And Mr. Bohr comes along and says, I can tell you why. Because the electrons are in a specific track. They're at a specific energy level. And what you see when you add energy to the hydrogen atom is you see them jump up an energy level. They stand on their desk. And then when they lose that energy, they give off energy in the form of light. And it's a specific set of wavelengths because there's a specific increment between the energy levels of ground and excited state. And so it's very, very much tied to that. So it's only defined paths. It's not the big Rutherford, anywhere they want to go, zipping around the nucleus. The Bohr model gives you these very defined paths. They can only be in those places. They can't be in between them. And to move up an energy level, you have to put energy into the atom. And when they fall back down, they give off energy, and that's when they glow. This is the model you learned in physical science. the Bohr model. And this is really just a modification of Rutherford, so it's sometimes called Bohr-Rutherford. Sometimes it's just called the planetary model. These are orbits, like planets orbit the sun. They are orbits. And it's great. And it worked really well for hydrogen. Except we have a bunch of other elements. Didn't work for other elements. So this model worked for hydrogen. It didn't work for bigger elements. Anything bigger. But it was a good stopgap measure. It was a good stopgap measure. Now we come along with Louis de Broglie. I always think he looks a little bit like a poodle. I don't know why. Whatever. But he's an incredibly bright physicist. He's French. And he looks at the work that Planck and Einstein did, and Einstein's idea of wave-particle nature of light. And de Broglie says, well, if light can behave as a wave and a particle, why can't electrons? So I want you to process this for a moment. Look at your hand. Your hand is made up of cells, and those cells are made up of atoms. And each one of those atoms in your hand has got little electrons orbiting its little nucleus. And you're made of matter, right? You are chunks of stuff. I know, it's such a romantic view of humanity. But you are a collection of chunks of stuff. What if I told you that your chunks of stuff were also waves? Like, this gets all kinds of cosmic and freaky. Like, you are stardust. No, you are starlight. Yes. All of your little electrons are behaving as waves at the same time as they behave as particles. And you know that we can write an equation for any wave if you've had any kind of math whatsoever. And so imagine all of your little electrons having little equations for their little waves. Now move your hand. Whoa! Isn't that cool? I like to give you things to think about on the long weekend. Hopefully, in the wee hours of the night when you wake up and you're staring at the ceiling, and then you just start going, ooh. Ooh, ooh, ooh. Science is the best drug out there. So, science is awesome. So, de Broglie says, no, you know what? Electrons are doing the same thing that light is. It's a particle, no, it's a wave. It's a particle, no, it's a wave. No, it's both! Well, if that's true, then we can write equations for everything. And if we have equations that have specific wave equations, then those frequencies might just correspond to the energy levels that Bohr suggested. This is all starting to fall together. This is starting to come together. I know, it seems really unrelated. This is the quantum stuff is so hard. De Broglie actually, when he wrote his doctoral thesis, and I think his doctoral thesis was before 1927, his thesis advisor got his doctoral thesis and said, you know what? I don't know enough to evaluate this. Why don't you send it to Einstein and see what he thinks? You know you're breaking new ground when your doctoral thesis advisor says, yeah, I can't really judge this. I don't know enough. Send it to Einstein. And Albert Einstein said of de Broglie, how did he say it? Einstein had a beautiful way with words. He has lifted a corner of the veil on the mystery of the universe. High praise, I'd say. So now we have this idea that these electrons are waves, so they have a formula, and because they are waves with a certain frequency, now they have an amount of energy because E equals hv and C equals lambda v. And so now we can put that together and we can fit them where Bohr thought. But how much would you pay for these Ginsu knives? Don't at the same time that all this is going on, and a lot of this stuff overlaps, and a lot of this, especially the quantum stuff, is not as sequential as everything else. Like all the basic structural stuff, finding the electron, finding the proton, finding the neutron, that runs in order. The quantum stuff jumps around a little bit. We kind of jump backwards because stuff that happened earlier influences things that are happening at the same time. So this is not a strict timeline presentation, you understand. So Werner Heisenberg is a physicist working in Germany, and and you may have run across the phrase matrix mechanics in regard to quantum stuff. I am not even going to attempt to explain matrix mechanics. I am not going to pretend to understand matrix mechanics. Way above my pay grade. Like, light years above my pay grade. I just want to have coffee and Kuchen with the man. Like, and a tasse Kaffee und a piece of Kuchen. That's fine. We'll sit for coffee in the afternoon and we'll chat about important things, I'm sure. But, and hike the Alps. So, what Heisenberg says that becomes really important, because for a long time there's actually sort of an argument, not sort of an argument, there's a big, fat, stinking, raging argument between these two, between Heisenberg and Schrodinger. Because Schrodinger is putting forth this quantum model with these wave equations, and Heisenberg is doing the matrix mechanics, and they think that they're doing different things, and it turns out actually no, they're saying the same thing differently. Whoops. Years of conflict. But what Heisenberg comes out with that's the really valuable contribution to this, he says, well, there's something important about an electron. You can't know everything about it at the same time. So, for me to observe this pencil, what has to happen? Tell me. I have to look at it, and does there have to be light? Light waves have to bounce off the pencil and hit my eye. Sounds very violent. For you to see anything, light waves have to strike the object and bounce back to you. If an object absorbs all of the light that hits it, it's invisible. And this is what a lot of the cloaking technology that militaries are working with is about, is creating the object that is the perfect sort of black body for light, that it just absorbs all the light around it. And then you can't see it. It's effectively invisible. Remember that light is acting as a wave and as a particle. And a particle of anything has some amount of mass. Well, electrons, you remember, are, as we said, really stinking tiny. So what Heisenberg says is, if you try to observe an electron, if you try to observe the position of an electron, your act of observing it, which requires a photon to strike it, changes it. The photon is enough to kick it out of where it is. So if you manage to observe its position, its velocity is going to change. And if you manage to observe its velocity, its position is going to change. The whole idea of the Heisenberg uncertainty principle is that the act of observing changes it. Okay, this is where I will share with you why I believe that the Heisenberg uncertainty principle is a metaphor for everything else in your life. And I want you to think about this for the rest of your life, because I have been since I learned it in my sophomore year of high school. The act of you observing a thing changes it. You being in the situation changes the situation. Well, what would have happened if I wasn't there? Well, we'll never know because you were. What would have happened if I wasn't there? Well, we'll never know because you weren't, or vice versa. The act of you being there makes it impossible to know what would have happened had you not. The act of observing a thing changes the nature of the thing. Holds true for jobs, family, relationships, friendships, everything else in your life for the rest of your life. Stick with Werner, you can't go wrong. So, yeah, the act of observing the thing changes it. So we can't ever pin down both where an electron is and how fast it's going. Now, this leads me to my first of my favorite Heisenberg jokes. Werner Heisenberg is speeding down the Autobahn. When suddenly, because that's what police sirens sound like in Germany. And he's pulled over on the Autobahn, and the officer, the Polizei, walks up to the car, knocks on the window. Herr Heisenberg, do you know how fast you were going? No, officer, but I know exactly where I am. I know you're trying not to laugh, but I know you really like that. Want me to do it again? Just so that you get it? Did you get it? Okay. At the same time that Werner's doing his work, Schrodinger, Erwin Schrodinger, we'll talk about the cat as a sidebar sometime, is working with this notion of electron waves. And he writes a series of equations. These are the Schrodinger equations. So you understand from math that we can write an equation that describes a line in space. We can write an equation that describes a wave in space on a coordinate system. You are typically dealing currently with a two-dimensional coordinate system, x and y axis. You understand that you're living on a three-dimensional coordinate system, yeah? The z-axis coming at you. Get it? You'll get it sometime this weekend and you'll laugh uproariously. So you can write an equation that describes a three-dimensional region of space. And that's what Schrodinger does. He writes equations that describe three-dimensional places. Well, here's the weird part. When he plugs in different frequencies for different waves, only some of them work. And that's when he starts to realize that what he's describing is not a general broad equation that fits any place, but these very specific regions. That's what gets us the quantum model. So the quantum model is what we work with now. And this is still changing, mind you. I mean, science is constantly changing. So the quantum model says this. Atoms have a dense central nucleus made of protons and neutrons. That has not changed. Little tiny hard-packed nucleus. Electrons are outside the nucleus. That hasn't changed. What has changed is, instead of the electrons orbiting on neat little racetracks, the orbits that we used to talk about, now we say that based on Schrodinger's equations, though we can't identify exactly where they are, we can never say, there's the electron, because it changes. Schrodinger's equations give us a three-dimensional region where there's a very high probability of finding an electron. And we call that an orbital. So we've gone from, this nice, neat little nucleus with the nice, orderly little electrons orbiting it that we taught you in physical science, which isn't a lie, but that's what we taught you in physical science, to the quantum model. And the quantum model looks like a golf ball that's been rolled inside about a Honda Civic's worth of cotton candy. The golf ball is the nucleus, the hard, dense, tightly little packed positive nucleus. And the Honda Civic's worth of cotton candy is all these orbitals. So we take all these three-dimensional regions that Schrodinger's equations describe, and they describe very specific shapes. And I will show you pictures of these shapes, and they are freaky, weird stuff. And we take all of those and superimpose them around the golf ball, and that's where we get the big cloud of cotton candy. We never know exactly where an electron is inside an individual orbital. And these are orbitals, that's important. Orbital, not orbit. Orbit is from the older Rutherford Bohr model. Orbital is the quantum model. So we never know exactly where they're at within an individual orbital, but we can tell you where there's a pretty good chance of finding them. So the corollary for this is like John Tomlinson. We can say that between 7:30 and 2:30, there's a good chance he is in Beaver Local High School. Can we narrow it down more? Yes, we can. We can say that between, 1:15, 1 o'clock, and, between 1 o'clock and 1:45, there's a really good chance that he's in room 24. Do we know exactly what desk he's sitting in? No, we're going to say we don't. But we can pin him down to a room, So we have a region where there's a high probability of finding John Tomlinson on any given day. That's an orbital. So this is the quantum model. It's a lot messier. We traded something really neat for something a lot messier that's probably a lot more like reality. Now, the question that always comes up. Well, so the quantum model's the correct one, right? It doesn't work that way. What's a model? It's a simplified version of reality. all it is. We make models all the time. Physical models, mathematical models, conceptual models. It is just a simplification. And the Bohr-Rutherford model is still a useful simplification. We teach it to you in physical science. And that's actually, that's standard practice. We sort of build you up to learning about the quantum model. So we look at that more simplified version, and then we go, oh yeah, really? No, it's a whole lot crazier than that. And it is. Is there more that we will know about the atom? Yeah, there will be. So we use both models still. In here, we will primarily work with the ideas from the quantum model. But, okay, that's where we're going to stop.